Welcome back to the deep dive. We're plunging into some really complex topics to bring you the essential insights you need.
Great to be here.
So today we're tackling this, well, quiet revolution that's reshaping how we build the foundations of our digital world.
That's a good way to put it.
I mean, think about it. Software development moves at lightning speed, right? But hardware design, it often seems to struggle to keep pace with all that complexity. There's this productivity gap.
Yeah, that's a well-known challenge in the industry.
So what if you could design powerful, really intricate hardware using the same languages you use for software, like C++, A?
And that's exactly the promise of high-level synthesis, or HLS.
HLS, okay.
It's a fundamental shift, really, in how digital systems are designed, especially those heading for, FPGAs and ASICs.
Field programmable gate arrays and application-specific integrated circuits. Got it.
Right. HLS acts as that really crucial bridge between the software world and the hardware world.
Okay, so our deep dive today is all about unpacking how HLS actually works.
Yep. We'll get into the nuts and bolts.
We want to explore the advantages it offers, which sound pretty massive, how designers are using it in practice.
And crucially, how they optimize those designs, getting peak performance.
Exactly. And we'll also look ahead, right, where this is all going, especially with the, explosion in AI.
AI is definitely a huge driver.
So by the end, you should have a clear understanding of HLS and why it's, changing the game in hardware development. Ready to dive in?
Let's do it.
Okay, so we've mentioned this productivity gap and the promise of HLS. Let's start right at the beginning. What is the HLS paradigm? How does it bridge software and hardware?
Well, at its core, HLS moves the starting point for hardware design way up.
Up the abstraction ladder.
Exactly. Instead of grappling with those really low-level structural descriptions, think Verilog or VHDL.
The traditional hardware description languages?
Right. HLS lets you work with high-level behavioral specifications. It allows designers to use languages they already know really well.
Like C, C++,
C, C++, BST, System C, even things like MATLAB in some cases. Languages they're comfortable with.
That sounds like a huge shift. So HLS isn't just like a fancy compiler then.
Yeah.
What's it doing beyond just translating C++ back?
No, it's much more than that. HLS, sometimes you hear it called C synthesis or ESL synthesis.
Electronic system level. Okay.
It automatically translates your algorithmic specification, your C++ code, into concrete register transfer level structures, RTL.
So it's inferring hardware.
Precisely. It's a sophisticated process. And the beauty is it frees designers to focus purely on the functionality of the correctness of their algorithm.
Instead of getting lost in the weeds.
Exactly. Without getting bogged down in what's traditionally been, the detailed, nitpicky, verbose, cryptic, and architecture-specific nature of writing RTL by hand.
I can imagine that's a profound relief for many. So what's the actual journey? Say I've written some C++ code. How does it become actual gates on a chip? Walk us through that.
Sure. It's a multi-stage process. First, your C++ code is analyzed by the HLS tool.
Taking into account any constraints I've set, like target speed or area.
Exactly. User-defined constraints. Then, the tool schedules all the operations in your code. This is critical. It transforms that untimed functional code.
The way you'd write it for a CPU.
Right. Into a fully timed, cycle-accurate RTL implementation. This RTL actually describes a specific microarchitecture.
Okay, so it's building a blueprint.
A blueprint with two main parts. A data path, that's the hardware that does the actual calculations, the adders, multipliers, memory.
The workhorse.
And a control unit, usually a finite state machine, or FSM, that's the brain, sequencing all the operations according to the schedule.
Got it. Data path and control, and then that RTL.
That automatically generated RTL then feeds into conventional logic synthesis tools. Think AMD's Vivado synthesis or Intel's Quartus Prime synthesis.
The standard tools engineers already use.
Right. And those tools map the RTL design down to the specific hardware primitives on the target device, the LUTs, the flip-flops, resulting in a gate-level netlist.
Ready for the FPGA or the ASIC fab.
Exactly.
Ready to become real hardware.
Okay. That abstraction advantage you mentioned. It sounds like a genuine game changer. But this productivity boost, what does it really mean in practice? Is it just writing less code? Or something more fundamental?
Oh, it's way more fundamental. It's not just fewer lines of code, although that helps. Think about verification. That's often the biggest bottleneck in hardware design.
Right, testing the design.
With HLS, you write a C test bench. You can simulate your design using that test bench in seconds or minutes.
Seconds compared to?
Compared to a traditional RTL simulation, which might take hours or even days for complex designs.
Wow. That's orders of magnitude.
Huge difference. This incredibly rapid feedback loop lets you validate your algorithm much faster, fix bugs quicker. It fundamentally changes how you iterate.
So you can try out ideas much more rapidly.
Exactly. You're not waiting potentially days just to see if your core concept even works.
That rapid iteration, that's where it gets really interesting, right? Especially with design space exploration, DSE. Ah, yes. DSE is one of the killer apps for HLS.
Because unlike RTL, where you kind of commit to one architecture up front
Right.
and spend ages implementing it,
Right. You build one specific thing.
HLS lets you generate lots of different hardware microarchitectures from the same C++ code.
Exactly. Just by changing these optimization directives, these little instructions called pragmas in your code.
Pragmas. Okay, we'll definitely come back to those.
But yeah, you tweak the pragmas, rerun synthesis, which is fast, and boom, you get a different hardware implementation, different trade-offs.
So you can explore trade-offs super quickly. Performance versus power versus area.
Incredibly quickly. You can ask those what-if questions. What's the area cost if I double the throughput? And get an answer in minutes, not weeks or months.
That's revolutionary. It turns HLS into more than just a compiler. It's like an architectural exploration engine.
That's a perfect way to describe it. It automates searching for that optimal hardware implementation for your specific needs. It's really powerful.
Okay, so we get the what and the why, but how does HLS, this sort of invisible architect, actually build the hardware from C++ware? You mentioned a cascade of sophisticated processes. What are those core steps?
Right, the core transformation. It involves several key stages. First, parsing the input C++ into an intermediate representation, or IR.
An IR, like compilers use.
Yes, very similar concept. Then come the crucial synthesis tasks: scheduling, allocation, and binding.
Scheduling, allocation, binding.
Okay. And finally, the tool generates the actual RTL code.
Let's unpack that, the intermediate representation. Why is that needed? Can't it just work on the C++ directly?
Well, the C++ code is first converted into an IR. Many modern HLS tools actually leverage existing compiler infrastructure like LLVM and its Clang front end for the initial analysis.
LLVM, widely used in software compilers.
Exactly. But LLVM's own IR is designed primarily for sequential software processors. Hardware is inherently parallel.
Okay. So it needs something more hardware-focused.
Precisely. So it's often translated, again, into a specialized hardware-oriented IR. Things like a control and data flow graph, or CDFG, or even newer formats based on MLIR.
And these specialized IRs, they explicitly capture parallelism and timing.
Yes, that's the key. They make the potential parallelism and the timing relationships explicit, which is absolutely essential for the synthesis engine to do its job effectively.
Okay, IR sorted. Then comes scheduling. You said earlier this is maybe the most critical step. Why?
It really is vital. Scheduling is where the HLS tool assigns every single operation from that IR, every addition, multiplication, memory read to a specific clock cycle, a specific control step.
So it's figuring out the timing of everything.
Exactly. And this assignment directly determines the design's overall latency, how long it takes to execute once, and also how much parallelism can actually be achieved.
And there are different ways the tool can approach this scheduling.
Yes, different strategies. There's unconstrained scheduling, like as soon as possible, or ASAP, which just tries to finish as quickly as possible, regardless of resources.
Fast as possible, maybe uses lots of hardware.
Potentially. Then there's time-constrained scheduling, where you give it a latency target, a deadline, and it tries to meet that while minimizing the hardware resources.
Okay, meet the deadline efficiently.
And the flip side is resource-constrained scheduling. You give it a fixed budget of hardware resources, say only 2 multipliers, and it minimizes the latency given those constraints.
Minimize time with fixed resources.
Got it. So once operations are scheduled in time, you need the actual hardware bits to perform them.
That's the allocation phase. After scheduling, HLS figures out the number and types of hardware components needed.
Like adders, multipliers.
Functional units, yes. Adders, multipliers, comparators, also storage elements like registers, and importantly, on-chip memory blocks like block RAMs or BRAMs.
And this choice depends on the target chip.
Yes, it uses a technology-specific library for the target FPGA or ASIC. And these allocation choices directly impact your final power, performance, and area of the PPA metrics.
Okay, scheduled in time, hardware resources allocated. What's next? Binding. Binding. This step maps those scheduled operations onto specific instances of the allocated hardware. So if you allocated 2 multipliers, binding decides which multiplication operation uses which multiplier instance at what time.
the actual assignment.
And a crucial concept here is resource sharing. This is really important for efficiency.
Resource sharing, how does that work?
If you have two operations, say two additions, that are scheduled in different clock cycles, meaning they don't happen at the exact same time.
They're non-overlapping in time.
Right. They can actually share the same physical adder hardware unit. The tool automatically inserts multiplexers to route the inputs correctly. This saves a lot of area on the chip.
That makes sense. Reuse hardware when it's free. It sounds like these three steps, scheduling, allocation, binding, are incredibly interconnected.
Totally. Deeply intertwined. You can't really optimize one without thinking about the others.
How so? Give me an example.
Well, imagine an inefficient schedule. Maybe it spreads operations out unnecessarily. That might force the allocator to instantiate more hardware resources than you actually need just because the schedule makes them seem busy.
Okay. Bad schedule forces more hardware.
Or, conversely, if your allocative functional units are slow, maybe you chose a small, slow multiplier to save area that will constrain the scheduler. It can't schedule operations any faster than the hardware allows, increasing your overall latency.
Right. Slow hardware limits the schedule.
Exactly. So often when you see poor performance in an HLS design, high latency, low throughput, the root cause is often some suboptimal decision made during these interconnected stages.
Which means analyzing the reports from these stages is critical for optimization.
Absolutely critical. You need to understand why the tool made the decisions it did.
Okay, and the final step in this whole transformation.
The final step is generating the actual RTL description, Verilog or VHDL code.
And that results in the data path and the controller you mentioned earlier.
Correct. The data path is built from all those allocated functional units and storage elements. It's the hardware that crunches the numbers. And the controller, usually that finite state machine, acts as the brain. It generates the control signals based on the schedule to make sure everything happens in the right sequence.
Okay, that gives us a solid picture of the under-the-hood process. Now let's switch perspective to the developer. What's the actual HLS workflow look like in practice? It feels like it must be iterative.
Oh, it's absolutely iterative. And the whole flow is designed for maximum productivity, really leveraging that ability to verify functionally at a high level.
So where do you start? Writing C++ bunch.
You start by writing your C or C++ function, the part you want to accelerate in hardware. And crucially, you also write a C++ test bench for it.
A test bench, just like in software development, to check if the function works correctly.
Exactly. And the first step is C-level simulation.
Okay, so you run everything on your computer first. What's the benefit?
You compile the C++ function and the test bench together and run it directly on your host machine using standard C++ compilers and debuggers like GDB or Visual Studio's debugger.
Ah, so you can use familiar software tools to find bugs.
Precisely. This validates that your algorithm is logically correct before you even think about hardware synthesis. And as we said, it's incredibly fast, orders of magnitude faster than RTL simulation.
So you get that fundamental logic right really quickly.
Yes. Rapid algorithm iteration.
Yeah?
Fast bug fixing. Get it right functionally first.
Okay, my C++ code works. The test bench passes. Now it's time for C synthesis, the translation engine.
Now you invoke the HLS tool. This is where it translates your verified CC++ function into RTL Verilog or VHDL.
Performing all that scheduling, allocation, binding we just talked about.
Exactly. Guided by your target clock frequency and any of those optimization pragmas you've added to your code.
And the output isn't just the RTL code, right? You get reports too.
Critically important reports. The tool gives you estimates for performance latency, initiation interval, and also resource utilization estimates. How many LUTs, flip-flops, BRAMs, DSP slices it thinks it will use.
These reports are the feedback for optimization.
They're your primary feedback loop, yes. You look at the numbers, see if you met your goals, identify bottlenecks.
Okay, you have the RTL, you have the reports. What's next? CRTL code simulation. Sounds important.
It's a vital verification step. It essentially checks if the hardware the HLS tool generated behaves identically to your original C++ code.
How does it do that? Does it use the same test bench?
Yes, that's the beauty of it. The HLS tool automatically uses your original C++ test bench. It sets up a simulation where inputs from the test bench are fed into the generated RTL module, running in an HDL simulator like ModelSim or Vivado simulator.
And it checks the outputs.
It compares the outputs from the RTL against the outputs produced by your original C++ function running within the same test bench environment.
Ah, so it's comparing hardware behavior against the golden C++ model.
Exactly. It's often called a correct by construction methodology.
Wow.
It significantly reduces the verification burden compared to writing separate, complex RTL test benches from scratch. Gives you high confidence.
Okay, verified RTL. Now you need to package it up and use it.
Precisely. IP, export, and system integration. The verified RTL is packaged as a reusable intellectual property block, an IP core.
Like a building block for a larger system.
Exactly. In the AMD world, it might become a Vivado IP core or a Vitis kernel object, an XSO file. For Intel, it integrates into Platform Designer.
And then you integrate it using graphical tools.
Often, yes. Tools like Vivado IP Integrator or Platform Designer let you visually connect this HLS-generated IP to other components, processors, memory controllers, etc.
Does HLS help with the interfaces too? Connecting it up.
Yes. The tools can often automatically generate standard interface logic like AXI4 Lite for control registers or AXI4 Stream for streaming data. They can even generate basic software drivers to interact with the IP.
That whole flow seems much faster than traditional RTL. But it raises a key question. If it's C++, why can't any C++ code work? You hinted at this. You're not writing for a CPU. Requires a mindset shift.
Absolutely. That's the fundamental thing to grasp. You're using C++ syntax, but you're describing a hardware architecture, not writing a sequential program for a CPU with infinite memory and an operating system.
So there's a specific subset of C++ that's synthesizable.
Exactly. HLS tools only support a specific subset. There are constructs that just don't map naturally or efficiently to hardware.
Can you give some concrete examples? What works and what doesn't? Let's start with memory.
Okay, memory. Static arrays, where the size is known at compile time. Generally fine, they can map to registers or BRAMs, but dynamic memory allocation?
Like malloc, free in C, or new, delete in C++ while fen, or standard library containers like std.vector.
Generally non-synthesizable. Why? Because hardware resources, the actual memory blocks, the registers must be fixed at compile time when the chip or FPGA is configured.
Wow.
There's no dynamic heap memory pool like in software.
Right? Hardware size is fixed. What about control flow? Loops, conditionals.
Standard stuff like fixed bound for loops, where the number of iterations is known, ifel statements, switch statements, those are all perfectly synthesizable.
But what about trickier things? Recursion.goto. System calls.
Generally not supported. Recursion implies a dynamic call stack, which hardware doesn't naturally have in the same way a CPU does. GoTo can create complex control structures that are hard to map efficiently, and system calls like printf or file IO,
They talk to an operating system.
which doesn't exist in your custom hardware block. So those are out.
Makes sense. What about object-oriented features? C++ uses classes and objects heavily.
Classes and structs used simply as data containers, usually fine. Member functions, often okay too, they can be synthesized, but more dynamic features.
Like virtual functions, function pointers,
Yeah,
heavy use of the STL.
those become problematic. Virtual functions involve dynamic dispatch, figuring out which function to call at runtime, which is complex in hardware. Function pointers can be tricky, and while some STL components might be supported with specific libraries, extensive use can lead to structures that aren't hardware-friendly or synthesizable.
Okay, and pointers, C and C and C++, are full of pointers. How does hardware handle them without that nice, unified address space software has?
Pointers are supported, but within limits. Pointers to top-level function arguments, like arrays passed into your HLS function, or pointers to local variables, like static arrays declared inside the function, are generally okay.
But not crazy pointer stuff.
Right. Unbounded pointer arithmetic, complex pointer-to-pointer structures, those often aren't synthesizable or lead to inefficient hardware. The memory model is just different. Arrays map to specific memory banks.
You also mentioned the volatile keyword being important.
Yes, volatile becomes crucial. It tells the C++ compiler not to optimize away memory accesses. In hardware, a memory location, like a control register or data from another module, might change unexpectedly from the outside. Volatile ensures the tool generates actual reads and writes every time you access that memory in your code.
Okay, so avoid the non-synthesizable stuff. But beyond that, are there best practices for writing good HLS-friendly code? Code that sets you up for better hardware.
Definitely. One of the most important, as we touched on, is using fixed loop bounds whenever possible.
Why is that so critical for the tool?
It gives the HLS tool complete information about the loop. It can accurately calculate the loop's latency, figure out dependencies, and perform really powerful optimizations like loop unrolling, which we'll discuss. Without fixed bounds, the tool's hands are tied.
Makes sense. What else?
Modular design is good breaking your code into smaller functions, but think about how they translate to hardware. Function calls have overhead, so use the inline directive judiciously.
Inline tells the tool to basically paste the function code in place.
Exactly. It avoids the hardware overhead of function call return logic. Good for small, frequently called functions, but can increase area if overused.
Now, this next one you mentioned is fascinating. Explicit data flow. This sounds like a major departure from typical software thinking.
It really is. In software, you might perform calculations in place, modifying data in an array directly. Think of a software FFT, maybe.
Right, overriding the input buffer.
Efficient HLS often requires a different approach. You need to rewrite algorithms to describe a streaming pipeline structure. You explicitly define how data flows from one processing stage to the next.
Like data moving down an assembly line.
Exactly. Often using special streaming data types provided by HLS libraries like hls.stream in the Vitis HLS world. Data goes in one end of a stage, gets processed, and flows out to the next stage.
So the C++ code isn't just the algorithm. It's fundamentally a description of the desired hardware pipeline.
You've got it. That's the core principle. You have to think about hardware parallelism and data movement while you're writing the C++ app.
Okay, so we know how to write code. HLS understands. Now the big challenge, making it perform. Getting speed, low latency, high throughput. This brings us to those optimization directives. The pragmas, these are the controls.
These are absolutely your microarchitecture controls. Pragmas are special comments or directives you embed right in your C++ code. They don't change what your code does functionally.
The logical result is the same.
Right. But they guide the HLS tool on how to build the hardware. They are your levers to directly influence performance, area, and power without rewriting the algorithm logic.
Let's break down the key ones. Pipeline. This seems fundamental for throughput. How does it work, and what's this initiation interval metric?
Pipelining is maybe the most important optimization for throughput. Think of it like an assembly line for your loop or function.
Overlapping operations.
Exactly. It overlaps the execution of loop iterations, or different calls to a function. Instead of waiting for iteration 1 to completely finish before starting iteration 2, pipelining breaks the operation into stages. Iteration 2 can start stage 1 while iteration 1 is in stage 2.
So you get results out much faster, more frequently.
Precisely. The goal is high throughput. And the key metric is the initiation interval, usually abbreviated as 2.
Initiation interval. What is that?
It's the number of clock cycles between starting successive loop iterations or accepting new inputs into the function pipeline. And 2 of 1 is the ideal goal.
I1 means you can start a new iteration every single clock cycle.
Yes. Maximum possible throughput for that clock frequency. A new input processed every cycle.
What stops you from always getting II1?
Dependencies. Especially loop-carried dependencies, where one iteration needs a result calculated in a previous iteration. That can force stalls in the pipeline, increasing the 2. Resource conflicts can also increase too if, say, you only have one memory port and need 2 accesses per iteration.
Okay, so pipeline for throughput. Next up, unroll. This sounds like trading area for parallelism directly.
That's exactly what it is. Unroll literally creates multiple physical copies of the loop body in hardware.
So instead of one set of hardware processing iterations sequentially or pipeline,
you get multiple sets of hardware working on different iterations simultaneously in parallel.
the main benefit being lower latency.
Yes. It directly reduces the overall latency of the loop because multiple iterations finish in the same time. It would take one or fewer to finish without unrolling.
But the cost is area.
The cost is a proportional increase in hardware resources area. If you fully unroll a loop of 10 iterations, you potentially create 10 copies of the loop body hardware.
And like pipelining, it can be limited by dependencies, especially memory.
Yes. Data dependencies between iterations can limit how much effective parallelism you get from unrolling, and very often memory access becomes the bottleneck. If all those unrolled copies need to access the same memory, they'll just queue up waiting for the port.
Which leads us perfectly to array partition and reshaping memory. This sounds absolutely critical. You mentioned default arrays map to single BRAMs, creating a bottleneck.
It's often the first thing you need to address for high performance. By default, an array in C++ might map to a single block RAM block on the FPGA.
And BRAMs only have 1 or 2 ports.
Typically, yes, meaning you can only read or write 1 or 2 elements per clock cycle from that entire array. If your pipelined or unrolled loop needs, say, 8 elements per cycle, you have a massive bottleneck. Your compute logic is starved.
So array partition breaks up the array.
Exactly. It splits that single logical array into multiple smaller, independent physical arrays or memory banks. Each smaller array gets its own access ports.
So if you partition an array into 8 smaller arrays.
You effectively get 8 times the memory bandwidth to that data, potentially. It dramatically increases the